Okay, so we've now seen how RSA should not be used. Now, RSA has the unknown weaknesses with all the padding stuff, and then you have the normal attacks where you're actually trying to break the system. So if you can factor, so the topic is now security of RSA. So if, let's call attacker Eve, if Eve can factor n and finds out it's p times q, then Eve can do the same computations that Alice was doing in setting up her secret, her public secret key pair. So if somebody can factor this number, then Eve can compute phi of n, and thus D inverse, well, sorry, E inverse, which is D mod phi of n. If on the exercise sheet you got fairly far and saw this MRSA problem, you had a similar question or had a similar attack where you also needed to invert something or something else, but that one was easy because it wasn't mod phi of n, it was mod n. And n you know. But the factorization of n, that's the tricky part. So let me make this as a comment for those who got this far, you understand it now. If you're doing more of the exercise sheet at home, then you will understand the comment later. In MRSA, we don't need to factor. We don't need to factor, so the attack is much easier. I mean, what I say on the sheet is break the system, and by that I mean like get the secret key or get a mechanism that you can always get the decryption of any ciphertext. Now, of course, we hope that when an attacker is confronted with RSA, they will just go like, factoring is hard. That's why I'm wearing the shirt today. And it also has a backside. Now, this plays better with American audiences, I know. So some years ago there was a speaking Barbie doll. And the speaking Barbie doll was doing all kinds of great things. And among those had one which really upset most people, namely, math is hard. Let's go shopping. Not a good thing. Now, of course, we had to make our joke on it, so Nadia Hanger made this shirt for me. And I told her, I'm not going to wear anything with a girly Barbie pink font and whatever. And of course, I'm wearing it today. So just for you, for the factorization, I'm wearing this special factoring is hard shirt. So that's where the let's go shopping comes from. It just means like, we expect the attacker to go up because factoring, unlike math, factoring is really, really hard. Well, not all factoring is hard, right? If I give you n is 1024, you can factor that in your head. You've seen this number before. You know that this one is 2 to the 10. So that's not hard to factor. If I give you 324, now it depends what I mean by factor. Do I mean factor completely, or just mean split into at least parts? I mean, for this one, I see instantly that there is a 2 in there. I actually see that there is a 4 in there, even an 8 is in there, because at some point I learned that, no, I see a 4. I know that if the last 2 digits, that number is divisible by 4, because 100 is divisible by 4, then I know it's divisible by 4. I also know that if the sum of all digits is divisible by 9, then it's divisible by 9. So this one I know is 2 to the 2 times 2 to the 3, 3 to the 2 times something. Now, it doesn't factor it completely because I'm too lazy to do long division here. Also, this is not really an RSA number. But generally, we mean splitting it into something smaller. For RSA, the only thing that makes it into something smaller is finding P or Q. For a random number that you find on the field, this is, well, easy to factor into something smaller and something else small. Actually, every second number is easy to factor, because it's even. More than that, if it's divisible by 3, you also find it. Divisible by 5, you find it. So many numbers are easy to factor. However, when you encounter an RSA number, you'll actually notice that you can encounter an RSA number because suddenly it's much, much harder to factor. So many numbers are easy to factor. So many numbers have at least some factors that are easy to find. So have easy to find. But if you give an RSA number, that is tougher. So we focus on RSA numbers. By which I mean we have two big factors. Now, one factorization method that I expect you all to know is trial division. Try 5, 2, try 3, try 5, 7. At some point you'll get there. So trial division will find a number after as many steps as the smallest of the factors. And if you're a little bit smart, you'll remember the Femoral Factorization, where you're crossing out multiples of 2, you're crossing out multiples of 3. You will not actually try 6 after you've tried 2 and 3. So you'll only try the next prime number that you know. So first method is trial division. So try dividing by all primes, and you'll find a solution after at most the square root of n steps. If you look at the two factors, the first factor must be smaller than the square root, while the other factor is larger than the square root. So after that many steps, you have found your factor. If you're getting a perfect square, you need to run as many as square root of n. This is a very simple algorithm. We're not going to do much more. If you ever find yourself in a situation that you want to factor a really big number, you will invest in trial division. Not because you're breaking RSA numbers per se, but because RSA numbers have as a subroutine something where you have lots of numbers that are like normal numbers, not like hard to factor numbers. So in breaking a big RSA number, you encounter lots of small factorizations. And for those, you need to optimize your trial division. So at some point I was, for a course, giving out Wikipedia projects, meaning, well, back then Wikipedia wasn't as good as it was now, so students could, instead of writing an exam, could make a Wikipedia page. And I had some Dutch students making a, I thought, really nice page on all kinds of factorization methods, including trial division. And then one of the Wikipedia editors for the Netherlands was like, this is too trivial. And unfortunately, that page disappeared. I was very upset because trial division is a very important method, even though it's very easy. That said, I'm not going to spend more time on it. Now, I need my sheets because the next numbers are looking rather wacko. So it actually takes effort to construct RSA numbers that are easy to factor and still RSA numbers. So weird RSA numbers. All right, how about n equals 1, 0, 0, 1, 6, 0, 0, 6, 3. First of all, what's weird about it would be, for me at least, that I'm seeing lots of zeros. It feels like somebody started with two numbers which themselves had lots of zeros and multiplied them. I mean, it could be just an accident, but it's much more likely that somebody who was making his RSA numbers was taking P and Q to both have lots of zeros. Now I'm getting a number which has 4, 6, 8, 9 digits. So this would be typically like some thousands times another thousands. So if I take the square root of n, maybe I just want to know how far I would have to go with trial division, or I'm becoming suspicious about all these zeros here, then that gives me 1, 0, 0, 0, 7 dot 9, 9, 9, 9, 5, 0. Now that's very, very suspicious. This is like so close to an integer. So when you see something like this, then you know this is very close to integer and has supplies the many zeros. This is very close to an integer and has many zeros. So I guess it's likely correct. Now the nice thing, if you're having a guess, you can just trial divide. I mean, trial division tells you, you pick a random number, well, you pick a small prime and try up. Now we can just trial divide by this thing. So if any of you has a computer out, you can just do this number by 1007. So if I compute n mod 1007, 10,007, I find out that that gives 0. So that means that I can divide without a factor. So I can divide n by 10,007 and anybody? 10,009 indeed. In your head or with the computer?
No, okay.
So if you see this thing here,
10,008.
you see this thing here, the 16.
Yes, 9 plus 7 and 9 plus 7 is 63.
Yeah. So you can actually do this one in your head. Now in general I wouldn't recommend doing big factorizations in your head, but this one is sufficiently easy and it's broken. Now this one was a very much cooked up example because I wanted something nice to factor. But in general, what we could do is we could start at square root of n, and then we just test for divisors. Let's call this thing m, And then we're checking n mod m, m plus 1, m plus 2, etc. Now, this in general is no better than trial division. I mean, this is just like, if you don't have a special number, this is not going to give us anything better. Again, you would need like the square root of steps, but this one helps against people who go like, I'm supposed to pick up two numbers. How about I pick one number, wherever I get the 10,007 from, and then I just say next prime. Because somebody told me I should take two primes of the same size. Well, yes, I said two primes of the same size, by which I mean same bit length. I do not mean next prime. That's really bad. So this one finds factors for n being p times next prime. And now it depends on your computer algebra system whether you have to say next prime p or next prime p plus 1. Well, p plus 1 definitely works. Sometimes next prime p will just give you p by saying it's the next prime larger or equal to p. So this is a useful command, but you shouldn't use it onto something under the attacker's control. So this one very easily finds factors for that. Now, a more systematic way is called Fermat factorization. And it says, well, we might not be able to find something really close to the square root, but if we are able to find NSE difference of two squares. So n is the number we want to factor. In these cases that we just seen, the 10,007, 10,009, we had that n was very close to 10,007 squared, and just a tiny bit less. So if we find A and B that satisfy this one, then we can use third binomial formula to say that n is equal, well, let's say it was equal here, to a plus b times a minus b. Okay, nothing interesting has happened yet. We've just expressed a squared minus b squared as a plus 1, a plus b times a minus b. But we also know that that is equal to p times q. Now, when you learn what a prime is, the normal definition that we tell our students or pupils at school is a prime number is a number which is only divisible by itself and by 1. But when you grow up and get into number theory, we tell you, well, that is actually a number which we would call irreducible. It can't be split. And for integers, it happens such that irreducible and prime are the same. But the proper definition of a prime is if a prime divides a product, it divides one of the factors. Now, if your normal habitat is the integers, these two things belong together. It's just totally the same. If 7 divides 21, then no matter how you split 21, one of the factors will be divided by 7. Because, well, 7 doesn't split. So you can't have like a part of 7 in the first part and a part of 7 in the second part. So 7 being prime means it needs to divide one of those two. Similarly here, p is a prime. So it must divide one of the two factors. Because P is prime, it divides A plus B or A minus B. And since I went for the easy version where n is equal to this, it can't be that Q divides the same. Because, well, n only has those two factors. If A is not the same as B, and I would please not have A equals B, else this would be 0. So I see that NQ divides the other. So the GCD of n with one of those factors, say A minus B, is a non-trivial factor of n. Okay? Now does this work? How do you get your squares? How do you find something nice like this? So, how to use this? For this class, I would say let's try luck. If you're staying on for the masters, we're actually going to do something more of how to build this. So, more in the course code is 2MMC10. Here, we only see luck cases. So for instance, totally random, and that's why I need the sheet. Our example is going to be n is equal to 5, 5, 0, 6, 5, 3, 1, 0, 7. Okay. Now this is not such a peculiar number that I was expected to see factors by just looking at it. But you could start by saying, well, I need to have something which is larger than the square root of n. So let's first figure out what the square root of n is. That for some reason I didn't put here, so I put it on my computer. And I realized I could have just copied it over. That's actually kind of stupid. Okay, the square root of this thing is 2, 3, 4, 6, 5, and then some stuff. 9, 9, something. Again, this is not just a lucky case, it's also a very constructed lucky case. So again, we are very close to some integer. So we need a to be larger than n, than the square root of n. So we first try a is next integer, so 2, 3, 4, 6, 6. Now when you compute the square of this one, what we're hoping for is that we find another square. So when you take a square and you subtracting n once, you're hoping to get a square. So compute a squared is going to something mod n. And now, since this is a nicely constructed example, this happens to be 49. Okay, so 49 I expected to recognize as 7 squared, and so we now have that A is this 23,466, and B is just 7. So B equals 7, A equals 23466, satisfies that we have A squared minus B squared is N. And so when you put this in, you're getting that A minus B, so this thing minus 7 is a factor, so one of the factors is 2, 3, 4, 5, 9, that is P, and we're getting the A plus B, which is 2, 3, 4, 7, 3, is equal to Q. And then you can generalize this by not insisting that it's equal to N, but it's congruent to N. So small generalization. Find A, B, with A is congruent, A squared is congruent to B squared mod N. So here I actually didn't need the GCD. Here I now really do need the GCD. And we want that A squared, that A is not the same as B. A trivial way would be to just take B is minus A, but then we don't learn anything either. So we want to have that A is not the same as plus or minus B. Then we take GCDs. And we're done. So, however you get this thing, I said, you're going to see this in the bigger class. We can actually build such relations, but that's more complicated. But once you have such a relation, the last step is super easy, just a GCD. One system which is easy enough for us to do here is the P-1 method. That's number 4, I think, yes. Now the P-1 method needs something that you have seen already when we proved RSA to work, namely that if you have some number to the phi of fit gives you 1. So this again uses little Fermat's little theorem. Namely, that if you have A, and we're looking mod P, then, well, phi of P is a prime. So A to the phi of P, that just means P minus 1. Because phi of P is P minus 1. So if we could compute some S which is A to the P minus 1, and now we compute mod N, then S would be congruent to 1 mod P, and S is congruent to something which is not congruent to 1 mod q. So we now look at the Chinese remainder theorem, but starting from a shared relation, going for the separate relations. So we know that S, if we take this thing and compute mod p, we're getting 1. And q is different from p, so we're getting something else. But it won't be 1. Unless your A is very special. For instance, A is 1 or has very small order, well, has order dividing p minus 1. For a normal A, this won't happen. And so what the p minus 1 method says is we compute, I shouldn't have now. We're computing the GCD of n with this S minus 1. So this will give us P, because then we have a 0 mod P on the right side, we have a 0 mod P on the left side, and it will not give us Q. But I've been cheating. You can't actually do this computation. I mean, I want to find P, and I'm putting it in as the power of A. I mean, it would work, but I would need to know P minus 1 in order to get P. Now, what the P minus 1 method does is, says, we hope, fingers crossed, hope that some large number, say the LCM of 2, 3, 4, till some k, and let's call this thing, what numbers are taken, let's call this thing R. Hope that this one is a multiple of P minus 1 and not of Q minus 1. So taking the LCM is one possibility, taking some predefined large number is a possibility. So the way that this R is computed depends on, well, what the person who implements it says he has higher hopes in. And then you compute S, which is A to the R mod n, and you compute the GCD of n with S minus 1. And this one, if in the case that it's divisible by P, it's a multiple of P minus 1 and not of Q minus 1, then this, again, is P. Now, there is no guarantee that any of your numbers will be like that. You have to be pretty lucky, but if nobody puts in anything special in the generation of P and Q, there are actually some chances that P minus 1 or Q minus 1 will have lots of small factors, so will be a multiple, the LCM will be multiple of it, and not for both of them. So if you don't have any specially constructed number to be secure against this, P minus 1 works. And of course, if I feed you any number and I say use the P minus 1 method, you can be sure that this number is constructed so that it works. So these are the methods we use for real, but if we do this for real in normal attacks, we have a far lower chance of these working. I mean, these are artificially constructed examples. On Monday I will start with a nice example for the P minus 1 method. Again, something which can work but doesn't have any obligations for working. All right, with that, nice weekend. See you Monday.